Welcome to Spring LIB.
So 36.92, we're talking about an experiment that involved measuring the moon's surface with a beam of light. There is a telescope on the Earth that's used to transmit the light, and then there's a mirror on the moon. We want to figure out what fraction of the original light makes it back, or is collected again by the same telescope. And so this is a little bit involved, but it's basically just keeping track of the ratios of the areas of each thing. So basically the beam of light will be larger, say, than the mirror, and so the fraction of the mirror the area of the mirror as a fraction of the area of the beam of light will be the efficiency of reflecting the energy if we assume the mirrors are perfect. So so D0 is the reflecting telescope's aperture on Earth. D1 is going to be the diameter of the light beam on the surface of the moon, so that's going to surround the mirror. And from the Rayleigh criterion, we know that it's going to be it's going to satisfy this. This is L is going to be the Earth-Moon distance. So this is 2 times the Rayleigh angle, which is 2 times 1.22 times lambda over d0. So then the fraction picked up, the fraction of the energy picked up by the moon on Earth is just going to be the ratio of the areas again, and we'll call this eta prime. So D2 is the size of the mirror on the moon, and D1 is the size of the beam of light on the moon. So basically we have the beam of light hitting an area larger than the mirror. So the fraction of this total area that the mirror takes up is the efficiency. Maybe easier to explain it with a little drawing there. So this gets reflected off towards the Earth, which has a cross section we'll call D3. Which again is a Rayleigh criterion thing. This will be 2 times 1.22 lambda now over D2, because that's our new aperture for the light's trip back to Earth. And so eta double prime is what we'll call that, or what we'll call the fraction of energy collected by the telescope on Earth that was reflected by the mirror on the moon. So D0 over D3 squared. D0, because we're using the same telescope to collect the light. D3 is the size of the beam on Earth after being reflected from the moon. And so the total efficiency of this is just the product of the efficiencies of each step. this is a little bit tedious, but it works out to be, well, not really tedious, but basically you put in the equations that we had from the Rayleigh criterion, and then you end up with d0 times d2. We can see pretty easily where that came from. And then we don't know d1 or d3, or it's not given to us, but it's going to be 2.44 lambda times another d here. And this is going to be to the 4th power. Oh, I see. Sorry, I was mixed up the notation here. This is L, the distance from the Earth to the moon. And so putting in our numbers for that, we get, this is 4 times 10 to the negative 13th. So it was probably a very high-powered laser beam that they shot at the moon to begin with, and then they must have had very sensitive equipment for detecting the return signal, given that this is, a lot of it was lost.